Welcome to this presentation on TinySec, lightweight security for sensor networks. TinySec is all about balancing strong cryptographic protection with extreme efficiency in resource-constrained environments. Imagine securing tiny devices that power the Internet of Things without draining their limited batteries or overwhelming their modest hardware. Let's dive into the challenge: securing resource-constrained sensor nodes. Unlike powerful servers, these tiny devices operate under extreme limitations, so security protocols must be designed with strict boundaries in mind. First, severe energy constraints. Battery life is everything. Every CPU cycle and transmitted bit eats up precious power, and complex crypto can drain batteries fast. Remember, the energy budget is critical. Communication costs are huge too. Wireless transmission uses way more energy than computation, so we must minimize packet overhead from security headers. Fun fact: transmitting one bit is about equivalent to 1000 CPU cycles. Then there's limited memory and processing. Tiny RAM, just 4 to 10 kilobytes, limits buffers, and slow 4 to 8 MHz CPUs make fancy public key ops impractical for frequent chats. Finally, lossy links and small MTUs mean packet loss is common, requiring retransmissions, and MTUs are often only 30 to 100 bytes, leaving little room for extras. Typical sensor mode specs include 48 to 128 kilobytes program flash and radio bandwidth from 19.2 to 250 kilobits per second. Now, why do existing protocols fail in this space? Traditional standards like IPsec, SSL, TLS, and SSH are built for power, assuming robust hardware, unlimited energy, and plenty of bandwidth. But look at the mismatch: packet overhead of 32 plus bytes, handshakes relying on PKI, RSA, or Diffie-Hellman, and memory usage in the megabytes for state. As the quote says, applying these to sensor networks is like trying to fit a jet engine on a bicycle. Critical failures include massive overhead. Standard headers can exceed a whole sensor packet of about 30 bytes, doubling or tripling energy use per message. Computational complexity is another killer. Public key ops take seconds on an 8-bit microcontroller, leading to latency and battery drain. Even early wireless sensor network proposals like SNEP were sound in concept but lacked full specs or real hardware implementations. The result? We need a clean slate design focused on link layer efficiency. Here's an overview of the TinySec solution. In the sensor node stack, TinySec sits at the link layer, right above the physical radio, securing communications transparently. It intercepts packets at the link layer, protecting routing data and application payloads alike, and sends protected app data straight to the radio, all without changing upper layer apps. It's designed for minimal expansion, using ciphertext stealing to ensure the encrypted data isn't longer than the original plaintext. Developers get configurable modes. Choose between TinySec Air for authenticated encryption when data sensitivity is high, balancing confidentiality and energy, or TinySec Auth for authentication-only to save power. Plus, the standard CRC is replaced by a 4-byte CBC MAC, detecting both transmission errors and tampering in one efficient step. TinySec offers 2 security modes for flexibility. First, TinySec Air, authenticated encryption. This encrypts the data payload and authenticates the entire packet with a MAC. It's the default for sensitive apps. It provides confidentiality to hide data from eavesdroppers, integrity to detect tampering, and authenticity to verify the sender's identity. The packet structure shows a header, encrypted data, and MAC, ideal for control signals needing the highest security. On the other side, TinySec Auth, authentication-only. This authenticates with a MAC but sends the payload in cleartext, useful when secrecy isn't required, saving energy. It skips confidentiality but still delivers integrity and authenticity. Packet structure: header, plain data, MAC, perfect for broadcasts with lower overhead. Moving to encryption design, TinySec uses an 8-byte initialization vector, or IV, structured for uniqueness across the network. 2 bytes for destination address, 1 byte for message type, 1 byte for length, 2 bytes for source address, and 2 bytes for a counter. Total 8 bytes, pre-encrypted to prevent info leakage. This efficiency balance means no need for random IV transmission with every packet. Most fields like addresses, type, and length are known from the header. It reduces overhead. The 16-bit counter prevents reuse, but there's a risk of reuse after 2 to the power of 16 messages. On the right, ciphertext stealing avoids padding by requiring ciphers to handle messages not in block size multiples, ensuring ciphertext length equals plaintext length, for example, turning 7 bytes of data into 7 bytes encrypted without extra bytes. Why choose CBC mode over stream ciphers? Stream ciphers were rejected because, while fast, they introduce vulnerabilities in constrained sensor networks. Catastrophic IV reuse. If an IV repeats, XO ring 2 ciphertexts reveals the plaintext XOR, breaking confidentiality. They require long IVs, say 16 bytes, to avoid reuse without state, creating unacceptable overhead. Malleability risks make bit flipping attacks easy unless heavy authentication is added. Verdict: too fragile for small IVs. TinySec's solution is CBC mode, cipher blockchaining, which offers robust security even with short, repeating IVs. It provides graceful degradation. IV repeat only leaks prefix sharing, not full plaintext XOR. Compact 8-byte IV is possible because CBC is more robust to reuse. IV pre-encryption prevents attackers from detecting identical IVs via the counter. Outcome: maximum security with minimal packet size. For block cipher selection, we evaluated candidates against 8-bit sensor constraints. Why others failed: triple DES is far too slow, needing excessive CPU for basics. AES offers excellent security but was slow on early Mica hardware with high implementation complexity. RC5 is very fast but was patented then and needed large RAM tables for keys. The chosen solution: Skipjack, TinySec's default after performance analysis. It's highly efficient, optimized for 8-bit architectures with minimal cycles per byte. Small footprint, low code size and RAM, no big tables like RC5. NSA declassified 64-bit block cipher with 80-bit keys, sufficient for sensor data without patents. It struck the perfect balance for the era. Authentication and integrity. Why encryption alone isn't enough. Attacks like bit flipping alter ciphertext predictably without the key. Cut and paste rearranges blocks from different messages to forge packets. Packet injection disrupts with fully forged messages. The solution is always on CBC MAC. TinySec computes a message authentication code using the cipher engine for efficiency, reusing it for every packet. The diagram shows length fed into encrypt, plus B1 encrypted to produce the MAC. It's a modified CBC MAC for variable lengths. The length fix: MAC equals CBC MAC of E_K, len, XORBO, B1, etc., with XO ring encrypted length preventing extension attacks, a vulnerability in standard CBC MAC for varying sizes. Packet format optimizations keep things efficient. Compare legacy packets: header, group ID, plain payload, 2-byte CRC. TinySec optimizes destination, AM, type, length, source, counter in cleartext header, encrypted payload for confidentiality, 4-byte MAC for authenticity. Early rejection: address, type, length, unencrypted so non-destination nodes discard immediately without decryption energy waste. Zero bloat removes legacy group ID, enforcing access via crypto keys instead of broadcast ID, saving a byte. Dual-purpose MAC replaces CRC with MAC, now detecting random errors and malicious tampering in one field. Our design philosophy: practical security for constraints. As the quote says, mechanisms must be lightweight yet robust against real threats, focusing on practical security tailored to sensor limits rather than max theoretical strength. Efficiency first: prioritize low CPU and memory primitives, like choosing Skipjack and reusing encryption for CBC MAC authentication. Link layer transparency: implemented at link layer for universal protection of headers and data, no upper layer changes needed. Configurable trade-offs: not one size fits all, pick auth only to save energy when secrecy isn't critical. Threat model centric: target realistic attacks like replay, forgery, eavesdropping, enabling optimizations like 8-byte IVs balancing safety and size. In conclusion, secure the smallest things. TinySec shows robust security doesn't need workstation resources. By tailoring crypto to hardware, we enable safe comms in hostile environments. Proven practical: minimal overhead proves link layer security on tiny moats without battery drain or bandwidth choke, thanks to optimized structures. Uncompromised security: Full confidentiality, integrity, authenticity, rejecting the idea small devices must be insecure. It's an IoT blueprint, a reference for securing billions of sensors instrumenting our world. Tailored design emphasizes specialized lightweight architectures for massive sensing, not porting heavy protocols like SSL, TLS.